Okay, so this is our second lesson on light, and if you are deadly confused already about what light is, don't worry, you're in good company. Like Albert Einstein and Isaac Newton, who spent a good chunk of their life trying to figure out how to describe light. So it's not easy to understand. Luckily, it is easy to understand how it acts. Most of you have experience with all these things, but we're going to try to come up with some good explanations for why light acts the way it does. This is what we're going to call the interactions of light. So how does it interact with matter? How does it interact with other waves of light? This is the objective for this lesson. So if you haven't already, please pull out your guided notes on the interactions of light, which are posted to the Google Classroom assignment here. We're going to be going through here, and then we'll provide a little bit of time at the end for review of that graphic organizer. Once again, those are not required, but I highly recommend you do them so we can keep track of the most important information from these slides. So waves can be disturbed. They're not crazy, but they're able to interact with things. We know that that's what waves are. That's one big evidence for why light is a wave in the first place, is the interaction of interference that we saw, right? So they can be changed when they come into contact with the boundary. And you have experience with most of these things already, but we'll go through them one at a time, starting with absorption. So light is able to be absorbed. So absorption occurs when light waves transfer energy to particles of matter. Taking a look at this diagram on the left here, this is just showing light coming in and then getting absorbed by, say, a piece of metal, right? That you might not see the light coming back off of that piece of metal. That's because energy gets transformed into something. You can take one guess at what that energy is that it gets transformed into is thermal energy. Most of the time, radiant energy comes to Earth from the sun and gets transformed into thermal energy when it's absorbed. When you're thinking about absorption, think like a sponge it's sucking up water, right? Except for this is a banana sucking up light. If the sun produces all forms of all wavelengths of light, right? Red light, orange light, yellow light, green, blue, violet. We call Roy G. Biv red, orange, yellow, green, blue, indigo, violet. If it's producing all those different types of light, but we're only seeing yellow coming back off the banana, right? You're looking at a banana, it's yellow because it's absorbing everything except for yellow. If a banana absorbed no light, it would look white, right? And some things that we eat are white, like cauliflower. Cauliflower does not absorb any of the light that the sun produces. It just shoots back out all of it at the same time, which is why it looks white to us. So it seems like I don't understand, right? But just think about this. If you're looking at a yellow banana, maybe it's a green banana, right? Just say yellow for now. Can you see it? Is it yellow? Yes. Well, there must be light coming into your eyes from the banana then, right? And that light must be yellow. And the second guess would be like, or the second check would be, well, is the light getting produced by the banana? Is this like a glowing banana? If it is, don't eat it, right? But that's not the case. It's just coming off of reflection from the light in the room, which is probably white light. If you think about a piece of paper in the room, if you see anything that's white in your room, that means that there's all those wavelengths of light that when put together just look white to us. I think we've talked about this a couple times. I am sorry for those people that were lied to for so many years when people told them that white was a color. It's not. It's just a mix-up of all the other colors that our eyes can't tell the difference between, so we see it as white in our brains. Okay, so absorption. When light comes in and hits the object, the vibration of the atoms is where that energy is going, right? It actually ends up hitting those atoms and causing them to vibrate more, causing thermal energy. Sometimes that gets radiated back out, like in the case of the ground. The sunlight hits the ground and gets absorbed by the ground, but then the ground throws that energy back out, right? And you feel it as warmth coming off the ground. Another good question would be like, why is it that on a sunny day you would rather wear white than black, right? Go ask somebody in your family right now, if they're not too annoyed at this point with all the questions I'm making you ask them. Or just think about it yourself. Why would you want to wear a white shirt rather than a black shirt on a hot sunny day in the summer? If you answered that the black shirt is absorbing all the different wavelengths of light that the sun's pumping out, so therefore it's going to be turning more of that light into heat, you are right. The white shirt reflects basically all the wavelengths of light. Now, maybe what would be even better is if you wore a mirror, but that would just be weird, right? A white shirt reflects a lot of that light without absorbing it, therefore it's going to be cooler. That doesn't really make a difference if it's not in a sunny time, it's just hot. That doesn't make much of a difference. It's the light itself that we're talking about here being turned into thermal energy when it absorbs into the fabrics. A longer explanation of this is here. If you want to see this, you can pause the video right now. I'll just try to read through it fairly quickly. When light hits a non-reflecting surface, the light waves are absorbed by the object. However, the light waves that are the same color as the object are not absorbed. Instead, those light waves bounce off the surface and are transmitted to the human eye and are basically interpreted by the human being to determine the color of the object. I'm sorry, it's cut off there. So, yellow bananas reflect only the yellow part of the sunlight that hits them, but absorb the rest of it. Same thing with apples. You see a red apple? It's because it's absorbing all the other forms of sunlight except for red. Now, the next interaction will be transmitted or transmission. Transmission is when light passes through something without interacting with it. So in other words, it's not going to be absorbed, but it's not going to be reflected off of it. It's just going to go right through it. We call that transmission. Now, we know that light doesn't like to travel through anything at all. It can travel through nothing, but when it does, usually as it interacts, one thing or another is going to happen to it. Either some of the wavelengths are going to get peeled away, or some of all the energy is going to get peeled away by absorption. Think about this as an example. Here's what you would call a red lens, okay, or a filter, it's also known as. If you had white light on this side shooting out all the forms of light, and it passes through this filter or lens, and on the other side of it, all you're seeing is red, what does that tell you about what's happening inside of that lens? It must be absorbing the other forms of light except for what you see, right? So if it's a red-looking lens, it must be absorbing green, blue, yellow, right? All the other stuff except for red. The same thing works with sunglasses, except sunglasses instead would take like most of all of this and just end up with not as much on this side, which would make it look more black, meaning that there's not very much light coming through at all, unless you have red sunglasses, which is totally awesome, right? When light hits an object and doesn't pass through it at all, we call that opacity or opaque. So this banana is opaque in a way that you can't see light coming through it, right? It's not like you can see the insides of the banana and the light on the other side of it. Same thing with a lunchbox or a book. So when that happens, we call it opaque. When some of the light is able to come through it, not all of it, we call that translucent. This would be the case for, say, sunglasses, which allow some of the light but not all of it to come through. And then some things just allow all the light to come through with very little interaction, and we call that transparent. So, you have a window pane that allows all the light to come through. That's transparent. Now, most windows don't allow all of it to come through. They just allow enough of it to come through that make it look like they do, while screening out things like ultraviolet radiation so you don't get sunburn or damage your eyes. But in general, we'll say that objects that allow light to pass through without changing the light are called transparent. This is just one more look at this. So take a second to think about how sunglasses work. We talked about it. So if you're looking on a sunny day, there's white light coming into your sunglasses. Why does it look so dark when you're looking through it then? Okay, the next one we're going to talk about is refraction. So refraction is another interaction that light does when it meets a boundary. This is kind of like transmission, but when the transmission through something is something that's more dense or less dense than what it was traveling through before. So at a boundary of two different mediums, say water and air or a vacuum of space and the atmosphere, you have light transferring through something that is more or less dense, it's going to slow down or speed up, depending on if it's going from something that's less dense to more dense, it will slow down. If it's going from something that's more dense to less dense, it will speed up. And what that looks like to us is a change in direction. Everything that we see is light, right? So if it slows down, it just looks like it's coming from a different place. It's very weird to think about, but we experience it all the time. If you ever have a spoon in a glass or a straw in a glass and it looks like it's broken, but you take it out and it's not, that's because as you put that into the glass of whatever it is, hopefully it's just water for this kind of a situation, it makes the easiest way of explaining it. You have the light is actually slowing down when it's going through, and so it looks like it's coming over from over here instead of from over here. If you have curved things that also change the direction of it because of the reflection angle or the transmission angle, that even makes it look bigger, say. But the reason it's broken is because it's coming from a different spot because it's slowed down. If it's more and more dense, it will even refract to a greater angle that makes it look like it's coming from a completely opposite angle even. It's kind of amazing. Take a second to think, how does this explain why rainbows work the way they do? I'll give you, it's not easy, right? But light does form a rainbow, right? We know that white light has all those colors present. Why is it that we can only see all those colors present, say after rain or when you have a prism like this? And the idea, once again, is refraction. When light travels in a rainbow, it's usually after rain, right? So there's more dense media up in here called water vapor. Water vapor is much more dense than the air around it. So as light travels through it, just like it does when it travels through a prism like this, it slows down once, changes direction, and speeds up and changes direction again. But in the process of going through these different things, it will also spread out. Think about red light as a less interactive form of light, right? It has a longer wavelength, it's less interactive because of that, less energetic. It's kind of coasting its way through this prism easily, right? However, blue and violet light, which are much more violent, they're going back and forth more often, so they get slowed down more often, right? It's like, who would get slowed down more often, quicker? Somebody that's walking through a swamp or somebody that's trying to run through it? And so this is like the people trying to run through the swamp, and red light is like the people trying to walk through the swamp. It's still going to get slowed down, but not nearly as much as this one, right? So they change direction, and by the time they get out really, really far away, you can actually see light broken into its constituent parts, the parts that make it up. Red, orange, yellow, green, blue, indigo, violet, all the colors of the rainbow. That's how refraction creates rainbows. All right, so this is one more look at this where the light looks like it's coming from here, right? But it's actually here. And the reason behind that is the refraction due to the dense medium here going into air and speeding up by the time it gets into your eyes. And it's not like it constantly speeds up, it speeds up at that barrier. It's important to note. All right, so we just learned about absorption, transmission, refraction. We learned why bananas are yellow, right? Why sunglasses work the way they do. We learned why rainbows happen. In the next lesson, we're going to talk about why is the sky blue? How about that? Come check it out, the second video, and then you can get going on to your exit ticket after that.